This video is about QR factorization of a matrix. We have three objectives. We're going to review the Gram-Schmidt orthogonalization theorem. We're going to prove the QR factorization theorem, and then we're going to do an example of doing a QR factorization of a matrix. Recall from the column vectors chapter, the Gram-Schmidt orthogonalization theorem. If we have a linearly independent set of vectors, S, v1, v2 up to vp, then we define some vectors u, uj given by this formula for j from 1 to p, and we let t equal the set of the vectors u and s is the set of the vectors v. The Gram-Schmidt theorem says that t is an orthogonal set of non-zero vectors and that the span of t is equal to the span of s. This expression is a bit complicated looking, so I've expanded it down here so you can see what the individual terms look like. Here's a new corollary to this theorem that we didn't see in the column vectors chapter because we had not yet studied vector spaces. The corollary says, given a basis B for Cn, here v1 up to vn, we define some vectors u the same way that we defined them up here. So these vectors are the same vectors u from the Gram-Schmidt orthogonalization theorem, and this set D that contains those vectors will be an orthogonal basis for Cn. The proof is very straightforward and follows directly from the theorem, which is why we call this a corollary. The theorem tells us that this set is an orthogonal set and that its span is the same as the span of B. Well, B spans Cn because it's a basis, therefore D also spans Cn. Furthermore, since D is orthogonal, it's linearly independent, and therefore, as a linearly independent set in Cn, it's a basis for Cn. All right, let's do an example that uses the Gram-Schmidt algorithm. Here we're given a matrix A, and we want to find an orthonormal basis for the column space of A. Well, to find a basis for the column space of A, we row reduce A and find the pivot columns. We can see the pivots here, and the corresponding pivot columns are 1, 2, and 4, and these columns form a basis for the column space of A. Now, to get an orthonormal basis, we're going to use the Gram-Schmidt algorithm to get an orthogonal set from this set, and then simply normalize those vectors to make them unit vectors and therefore an orthonormal basis. So we'll just name these vectors v1, v2, v3 down here, and then we use the Gram-Schmidt algorithm from the theorem. The first vector we get for free, u1, is just equal to v1. And then we use the formula for u2. u2 is v2 minus this expression. For now, this is just a formula, but as we'll see later, this is the projection of v2 onto u1. So we're subtracting from v2 its projection onto u1 to make it orthogonal to u1. Here are the details, and we get this vector. So here's u2. We use the formula for u3. We subtract from v3 the projection of v3 onto u1 and the projection of v3 onto u2. Here are the details to get u3 here. Okay, that gives us an orthogonal basis then. So all we have to do is normalize these three vectors to get an orthonormal basis. We'll define some W vectors to be the corresponding U vectors divided by their norms. So W1 is U1 divided by the norm of U1, etc. And we can see the calculations here. For W1, we compute the norm of U1, which turns out to be root 6. So we simply divide U1 by root 6 to get W1. The norm of U2 is root 3. So we divide U2 by root 3 to get W2. The norm of u3 turns out to be 1 over root 3, so we divide u3 by 1 over root 3, or simply multiply u3 by root 3 to get w3. And then we have our orthonormal basis for the column space of A. As I mentioned earlier, here are the details of all the calculations in that previous example, all the dot products and the norm calculations for reference. Now we come to the main topic of this video, the QR factorization, and we'll start off with the main theorem. If A is a real n by n matrix with linearly independent columns, then A can be factored like this. A equals Q times R, where Q is an m by n matrix whose columns form an orthonormal basis for the column space of A, and R is a square n by n upper triangular matrix that's invertible and has positive entries on its diagonal. You could think of this theorem as describing what happens if you take the matrix A, do the Gram-Schmidt process on its columns to produce the matrix Q. In other words, Q will be the matrix A with its columns orthonormalized. And this theorem tells us the relationship between A and Q. And in particular, A is equal to Q multiplied by this square matrix R. And R has some very specific characteristics. It's invertible, it's upper triangular, and the entries on its diagonal are all positive. Especially because R has such specific characteristics, the proof will be a little bit involved since we need to show all of these things. All right, we'll start the proof by writing A like this. We'll label the columns of A, V1, V2, up to Vn. Then we'll put those column vectors into a set B, and since this set is linearly independent, A has linearly independent columns, therefore B is a basis for the column space of A. Then I'll perform the Gram-Schmidt algorithm on B and normalize the vectors that I get to produce this set D, and by corollary 1.1.1, D is an orthonormal basis for the column space of A. Now we're going to consider the kth column of the matrix A, which is V sub k, since I've called the columns of A V's up here. Well, V sub k, of course, is in the span of the set containing V1, V2, up to V sub k, because it's in the spanning set. And theorem 1.1, the Gram-Schmidt theorem, tells us that the span of this set is equal to the span of this set. So I can write V sub k as a linear combination of the vectors in this set, which I've done down here, for some arbitrary real numbers, R1k, R2k, up to Rkk. It may seem strange to have two subscripts on the coefficients here, but it'll make sense why we did that as we go on. Remember that one of the conditions on R is that its diagonal entries are positive, and it will turn out that this coefficient here, Rkk, will be one of the diagonal entries of R, and so we want to ensure that this number is positive. Well, the only thing we know about these R's right now is that they're just some arbitrary real numbers. They could be positive, negative, or zero. We want to ensure that they're non-negative, so we'll say if Rkk is negative, simply multiply it and uk here by -1. So we're multiplying by two factors of -1. We're not changing this term. U sub k will absorb one of the negative ones, and then the other -1 will change Rkk from negative to positive. And so that way we know that it's greater than or equal to 0. It still might be 0, but we'll deal with that later. All right, so we've got V sub k written as a linear combination of U1 up through UK. What we really want, though, is V sub k written as a linear combination of the entire set D, U1 up through UN. Since A has n columns, k has to be less than or equal to n. So I can write V sub k as a linear combination of the entire set D just by adding some 0 terms like this. So here's V sub k with these terms up here as the first k terms in this expression. Then I just add 0 uk plus 1, 0 uk plus 2, etc. up to 0 un to get vk written as a linear combination of all of the u's in this basis D. The reason I want to do that is so that I can define this vector r sub k to be the vector of all those coefficients, r1k, r2k, up to rkk, and then the rest of them, this would be rk plus 1k, rk plus 2k, down to rnk. Those are all zeros. And then using the definition of a matrix vector product, we can write that linear combination that we saw here as a matrix times a vector. Remember, the definition of the matrix vector product says you take the entries in this vector and multiply them by the columns of this matrix and add them up. So here are the entries in the vector, and what they use as the columns of the matrix. When we do that, we get the linear combination that we just saw. Now we're just going to label this matrix Q, and then we're going to put all of these vectors R1, R2, up to Rn into a matrix and call that R, which will look like this. And notice it's upper triangular. The lower triangle is all zeros. So I've labeled this matrix Q, so I can write VK is Q times RK, which I've got down here. And that means I can write A by replacing the V's with this expression. So V1 will be QR1, V2 will be QR2, etc. Vn will be QRn. Well, using the definition of a matrix product, this expression is simply Q times R. So there is our QR factorization. Clearly, the columns of Q form an orthonormal basis for the column space of A because of how we defined Q. Remember, the U's are the orthonormal basis vectors for the column space of A. But what about R? Well, R is upper triangular. Is it invertible? To see that R is invertible, we can consider this equation, Rx equals 0. Remember, R is a square matrix, so if the only solution to this equation is the trivial solution, that means by the invertible matrix theorem that R has to be invertible. If we multiply both sides of this equation by Q on the left, well, Q times 0 is still 0, but QR is equal to A, and since the columns of A are linearly independent, that means that the only solution to this equation is indeed the trivial trivial solution, x equals 0. So R is invertible. What about the entries on the main diagonal? Here are the entries on the main diagonal. Well, we know from before that they're not negative. None of these can be negative. But what about 0? Could any of them be 0? The theorem says that they have to be positive, so they can't be 0. Well, because R is invertible, we know its determinant is not 0, again by the invertible matrix theorem. And because R is upper triangular, we have a theorem that tells us that the determinant of R is equal to the product of its diagonal entries. Well, if the product of all these numbers is not 0, that means none of these numbers can be 0. So we can conclude that the diagonal entries, not only are they non-negative, they're also non-zero, therefore they are positive, and that finishes the conditions on R, which finishes the proof of the theorem. Okay, let's do a QR factorization example. Here's a matrix A. We're asked to do a QR factorization of A if possible. Remember, it is only possible if the columns of A form a linearly independent set. How do we figure that out? Well, of course, we row reduce it and see how many pivots there are. In this case, we can see we got 3 pivots. Therefore, the columns form a linearly independent set, and we can indeed do the QR factorization. Well, how do we do it? The first thing we need to do is find the matrix Q. So we need to do something like the first example that we did in this video. Given a matrix A, find an orthonormal basis for its column space. Well, if you look back at the previous example, you'll notice that these 3 columns are 3 of the columns from that previous matrix A. If we look back at A, we can see that these are the 3 columns from this matrix A that are in the new matrix A. And we can see here that they were the pivot columns of this matrix A. So of course, they're going to be the pivot columns of the matrix that just contains these 3 vectors. Because these are 3 of the same columns from the previous example, we can recycle a lot of that work to find the orthonormal basis for the column space of A. We'll do the same thing we did before. We'll label the 3 column vectors v1, v2, v3. So this is a basis for the column space of A. We do the Gram-Schmidt process. You can see the details in the previous example, and we'll get this orthogonal basis, which is the same orthogonal basis we got in the previous example. And of course, when we normalize it, we get the same orthonormal basis. Well, here's our orthonormal basis for the column space of A, so we simply take these 3 vectors and put them into a matrix, and there's Q. So we've got Q here. Now, how do we find the matrix R? Well, we could look at the proof of theorem 2.1 and how R was constructed there and try to construct R for this specific example, but there's an easier way. Q is not a square matrix, so it's not orthogonal, but its columns are orthonormal, so it still satisfies the property that orthogonal matrices satisfy. In particular, Q transpose Q is equal to the identity. And we can use this to derive a formula for R. If we just multiply A on the left by Q transpose, we can replace A with QR, and then Q transpose Q is the identity, so the identity times R is just R. And that gives us a handy formula to use to calculate R. All right, so substituting for Q transpose and A in the example that we have here, here's Q transpose, here's A, we multiply the 2, and that gives us R. Notice that R is indeed square. It's 3 by 3. A was a 4 by 3 matrix, so N is 3 in this case, and R is 3 by 3. It's upper triangular. The lower triangle here is all zeros, and the entries on the main diagonal are all positive. So R satisfies all the conditions of the theorem. We can check the result simply by multiplying Q and R to confirm that we get A back. So here's Q, here's R, multiply them together, and indeed we get A. And so our QR factorization is correct. That finishes our video on QR factorization. We reviewed the Gram-Schmidt orthogonalization theorem, proved the QR factorization theorem, and did a QR factorization example.